Today we're going to be looking at three methods to find the area of an ellipse. Okay, three methods that do work, and then we're going to look at one that doesn't work, which is quite surprising, but one that is a fairly common trap that people can fall into. Okay, so all we need to do, we have an ellipse here, x squared over a squared add y squared over b squared equals 1. Here it is, so that is the point here, a 0, and this is the point here, 0b, and this is the point here, minus a 0, and this is the point here, 0 minus b. And what we're going to do is, the first method we're going to do is actually very cute, I think. So what we're going to do is we're going to just take a unit circle here. So let's draw our unit circle here, which is supposed to be centered at the origin. Now as that has a radius of 1, its area is pi times 1 squared, which equals pi. And then what we're going to do is we're going to use our linear translations, and we are going to stretch the circle by a factor of a that way, which is going to increase the area by a, and then we're going to stretch it by a factor b that way, and that's going to increase the area by a factor b. So the area will become pi a b, and our unit circle, which is x squared add y squared equals 1, when we stretch it by factor a in the x direction, we replace x by x over a, so that gives us x over a squared, and when we replace by a factor b in the y direction, we get y over b instead of y equals 1, which is exactly the same as that. And so basically we have used the area of a unit circle to find the area of an ellipse, which is pi ab. That's a cute way of doing it, and that's the first way. But the second way and third way, we're going to use double integrals. The first one Cartesian, and the second one will be polar. So okay, so basically let's have a look, and we're only going to look at this segment here, and then we're going to use symmetry to just multiply by 4, and that will give us the area of the whole thing. So what we're going to do in double integral, we're going to have double integral of 1 dy dx, and that will give us the area. And now as x squared over a squared add y squared over b squared equals 1, then we have 1 minus x squared over a squared equals y squared over b squared, i.e. y equals b over a root a squared minus x squared. Okay, so basically we know our point here is going to go from the point y equals 0 up to here, y equals b over a root a squared minus x squared, and we know that it's going to go from x equals 0 all the way through to a, so we can put our double integral limits here, and then this one here will be y equals b over a root a squared minus x squared, and y equals 0. So we now have our double integral, and obviously the first bit is simple, so basically that becomes the integral x equals a and 0 of b over a, taking the b over a out, root a squared minus x squared. Now in actual fact you could do this as a single integral, but we might as well do it as a double integral because we can compare it to the polar method. So we have that as our integral now. So what we need to do is we need to use substitution. So let's put x equal a sine theta. So dx equals a cos theta d theta, which means that this integral here becomes b over a, the integral between theta equals pi over 2, sticking a into here, and theta equals 0 of root a squared minus a squared sine squared theta times by, instead of dx, we have a cos theta d theta. This is just integrating by substitution, which equals b over a integral theta equals pi over 2 and theta equals 0 of, well, that will be a root 1 minus sine squared theta times a cos theta d theta, and that is just cos theta. So basically taking everything out of here, that gives us ba over 2, ba, the integral between theta equals pi over 2 and theta equals 0 of cos squared theta d theta, and using 2 cos squared theta equals cos of 2 theta add 1, we can therefore replace that as equals ba over 2 integral between theta equals 0 and pi over 2 of cos cos 2 theta cos, sorry, I don't write the cos very well, do I? Cos 2 theta add 1 d theta, which equals BA over 2 sine 2 theta over 2 add theta between pi over 2 and 0, and hopefully that is going to give us, and that gives us BA over 2, well, sine of 2 theta will be 0, 0 add pi over 2 minus 0, which equals pi AB over 4, which equals 1/4 of what we found by our cube method, and multiply by 4 because there are 4 identical parts of the symmetry, and that gives us the area of the ellipse is, again, pi AB. So that's method number 2, and that's integrating with Cartesian coordinates. Okay, so now let's integrate with polar coordinates. So if we take any point on here as x equals r cos theta and y equals r sine theta, and by the way, even though a parameterisation of the ellipse is a cos theta and, or let's use different t and b sine t, this is one of the methods that doesn't work, and we'll do that in a minute. So we use this parameterisation here, where theta is, well, you can't see at that angle there. Okay, so what we're going to do now is that will be, so we have x squared over a squared add y squared over b squared equals 1, and we have, as we just said, x equals r cos theta and y equals r sine theta. So what we need to do here is we need to put these into here. That gives us r squared cos squared theta over a squared add r squared sine squared theta over b squared equals 1. What we need to do now is just get r as the subject there, so that's b squared r squared cos squared theta add a squared r squared sine squared theta equals a squared b squared, i.e. r squared equals a squared b squared over b squared cos squared theta add a squared sine squared theta, i.e. r, finally, equals ab over the square root of b squared cos squared theta add a squared sine squared theta. Okay, finally, so now what we want to do is we want to do our double integral in polar coordinates. Okay, so that is the integral of 1. Remember, we've dealt with this in previous videos, we replace dx dy by r dr d theta, and that's how we do it in polar coordinates. Okay, so basically we want the integral r equals 0 to this thing here. I won't rewrite that, there's not enough space. And then we want theta, because we're only going to be doing, if we look at our ellipse here, we're only going to be doing this quadrant here, and then we'll multiply by 4. We want theta from 0 to pi over 2, so that would be theta equals 0 to pi over 2 of 1 r d theta, and that equals the integral between theta equals pi over 2 and 0 of r squared over 2 d theta, and we can now plonk in between 0 and that value there, which I'm not going to rewrite again. So that equals the integral between theta 0 and pi over 2 of a squared b squared. What we're doing is we are now squaring this, a squared b squared, and take the half out, a squared b squared over b squared cos squared theta add a squared sine squared theta d theta. And that's what we've got to integrate now in the polar form. Okay, so basically what we need to do here is whenever you've got anything of the form cos squared theta add sine squared theta on the bottom, what you want to do is divide everything by cos squared theta. And the reason being is that, well, we'll see, let's just write it down. So that's theta equals 0 to pi over 2. And we're going to divide top and bottom by cos squared theta. And 1 over cos squared theta is sec squared theta. So that is going to give us, and I'll take the a squared b squared out as well, make it easier. That's going to give us sec squared theta over b squared, because cos squared and cos squared, add a squared tan squared theta d theta. And we can see, why are we doing this? Well, because the derivative of tan is sec squared, and so this is going to be the way that we're going to be able to do this integral. So now we're going to have to use another substitution, let u equal tan theta, so therefore du equals sec squared theta d theta, which is how we're going to solve that top bit. And that's going to be now equal to, and also what we're going to do is we're going to divide everything through by this a squared, and you'll see why in a minute. So basically we'll get rid of the a squared there, and that will be b squared over a squared add tan squared. So all I've done is I've moved the a squared in, just so it's in a form where we can now integrate it. So that equals now b squared over 2. The integral, okay, so we need to change our limits. Well, u is tan theta, so tan of pi over 2 is infinite, and tan of 0 is 0. So that's u equals infinity down to 0 of du, which is basically that bit there on the substitution, over b squared over a squared add u squared. Now this is a well-known integral. And basically this integral equals b squared over 2, 1 over b over a, which is that bit, times tan to the minus 1 a u over b. That's the known integral there between infinity and 0. Okay, so basically now that gives us, sorting this out, that's a over b, so that gives us ab over 2, the integral of tan to the minus 1 au over b between 0 and infinity, which gives us, well, infinity, the angle whose tangent is infinity is pi over 2, and so therefore that gives us ab over 2 times pi over 2, which equals pi ab over 4, which again is the area of the quarter segment, where are we? Here. And so therefore the area of the whole ellipse, again, is pi ab, doing it by polar coordinates. Okay, so now finally the last way, and this is the way that you can't do it. Okay, so we know that, let's try and draw an ellipse. It probably won't be very good, but let's try and draw an ellipse and see what it comes out like. Oh, that's not bad. Not bad at all. Quite impressed with that. Okay, so here is our ellipse here, and we use the coordinates with the central angle here, theta, of r cos... Oops. Oh dear, sorry, I spoke too soon, didn't I there? Well, I don't know what happened there. Let's go back to it. So we used r cos theta, r sine theta as our coordinates. Now there is also a parameterisation of an ellipse, which is x equals a cos t and y equals b sine t. And you might think, well, why can't we just use this and use this as our polar coordinates here and integrate between t equals 0 and pi over 2 exactly the same way as we've done? That will give us the area of the ellipse. The problem is that polar coordinates, when you integrate it, the angle which you're using in polar coordinates must be this central angle here. Now in actual fact, if we put these coordinates in here, so that this here is equal to b sine t, and this, this here is equal to a cos t, then we have that the tangent of the central angle theta is equal to b sine t over a cos t, which equals b over a tan of t. So you can see that the tangent of the theta, the central angle of the ellipse, is not the same thing as the angle t. It's not the same thing at all, and therefore you cannot use this angle t to integrate in the polar form. So when you're integrating double integrals or whatever in polar form, you're very strongly advised to use this parameterization, r cos theta, r sine theta, for ellipses or for whatever, rather than possibly more familiar parameterizations, because you would have to convert this parameterization here to one where it was the central angle, and that would actually bring us back somewhere to about here. So it would actually be the same thing. But what you can't do is just use t as your central angle, because it's not the central angle, because you would get the wrong answer. Okay, well, I hope you found this useful. If you did, please subscribe to the Gresty Academy YouTube channel and press the little thumbs up button. Thank you.